it's on.
I think now it's on.
Okay. Is that mostly for online or also here in the room? Can you hear me okay, everyone in the back? Okay, good. Yeah, yeah. And maybe also checking online if you can hear me okay?
Yeah.
Very good. Thank you.
Since it's two and I think Leo will be chair, but since it's not here, I think I'm just gonna so I'd like to welcome Witek from UIUC, and she'll be talking about numerical relativity modified gravity.
Okay, thank you so much, Johnny, and thank you everyone for coming back after lunch. And now we want to continue with our applications of numerical relativity, now thinking about applications in fundamental physics. I put modified gravity, but I will also actually think about what happens if I add new light fields that are interesting in the context of particle physics. So really think about this numerical relativity applications in fundamental physics. And let me also just get rid of these here. Okay, very good. And what I want to do today is talk about three things. The first one is to talk about our software that is called Canuda, that really works in conjunction with the Einstein toolkit and is an open source software for numerical relativity with applications in fundamental physics, which thinks about modified gravity, general relativity with extra fields. We can also use it to just evolve black holes in general relativity. And I give you a little bit of an overview on the structure of the code. So for that, maybe I can get a quick hands up who is extremely familiar with the Einstein toolkit and has used it on a daily basis for their work. Okay. Who has run the Einstein toolkit but hasn't really looked at the thorns underneath, so more like a black box? Okay, and who is completely new? Yay, welcome to the community. Okay, so whenever I say anything that is not familiar to you, please just raise your hand and I'm happy to clarify. Okay, very good. Yeah, so this will be the first part. And then I want to talk about two applications. The first application is about black holes and very light scalar fields. So fundamental fields that are interesting in the context of particle physics, and I will talk a bit about that when we get there. And then this last part will be about black holes in extensions of general relativity, and we will look at a specific class of those. Okay, and yeah, I would say if you do have any questions, let me know. Johnny is also monitoring the chat if there are any questions online, so please just let me know. Good. Also, big shout out to my group in Illinois, because a lot of the students and postdocs have done some of the work that I will present today. Deborah is here. Everyone else not this week, because actually Ching Ching is working with Vasilius in Oak Ridge for the summer as an internship. But also I put up his name here in color because he will be applying for postdocs in the fall. So if you want to get an expert on numerical relativity who is really developing next generation Einstein toolkit, remember his name, he's really good. The other name I want to highlight here is Chloe Richards, who has done a lot of the work in modified gravity, written the code for that. And again, she is going to apply for postdocs this fall. So both, I think, are fantastic, and there's a big shout out to their work. Good. So the code that we are using, as I mentioned, is called Canuda. And this is a pretty busy slide, so let me just go by it. This is a list of authors as of 2023. We're actually currently updating and preparing a new Zenodo data entry to give credit to all the work that has gotten into this since then. And Canuda is this open source numerical relativity code for fundamental physics. Here's our Zenodo DOI. So if you ever use Canuda, you're welcome to do so, but please do cite the DOI, because that gives credit to all the people who have been in the development of that code. Also, as I already said in the beginning, it's really based off the Einstein toolkit, has exactly the same code structure as the Einstein toolkit. Thorns, as we call our modules, and the Bitbucket link is here. We also have a YouTube channel where you can see some of our animations. And if you think about some of the applications, well, I didn't put the black hole binaries in general relativity that we can do but a lot of applications are thinking about modified gravity here, like black holes in dynamic Simons gravity, or scalar Gauss-Bonnet, which are quadratic curvature extensions of general relativity, extra fields. Here are also works using our code in the context of boson stars, extra fields. And actually, if you have used Canuda and want your work shown up there, please let me know. Yeah, so I would be very happy to showcase your work as well. So let me know about that. And the other thing is there's a lot of pictures here, but I really want to focus on two things. The one is black holes and scalar fields, and the other one is modified gravity. Now, one thing that I added this morning to give all of you a bit of an idea was what is actually included in Canuda. I decided to come up with the following slides. So we already talked about thorns as being kind of code, or the tiniest code modules that we have. For a specific problem, we will have a collection of these thorns, or a collection of these modules, and we call those arrangements. And we have several of those. The ones that are officially in the Einstein toolkit will have an asterisk. The others I will mention as well. So the first one is called lean public, and this is our space-time evolution code, where we have a thorn that really involves Einstein's equations in the Baumgarten, Shapiro, Shibata, Nakamura formulation with a puncture gauge. We also prepare care in quasi-isotropic coordinates as analytical data. So you can either use this as initial data for a single black hole, or we oftentimes use that as our background spacetime to then look at scalar or vector field perturbations around those. So that's in there. It's also pretty readable. So if you ever want to read and learn how to write the code, it actually might be a good starting point. And then we also have wave extraction, thorn, NP scalars for Newman-Penrose scalars here. And we've compared this with other thorns available in the Einstein toolkit to benchmark and make sure that they are giving correct results. Then we have an arrangement that's called scalar. I will talk about this in a little bit more. Essentially what it does is evolving a complex scalar field that can potentially be coupled to general relativity. And it's also in the Einstein toolkit already in the public version. We have an arrangement called Proca. Proca field is a massive vector field. And again, this is already public in the Einstein toolkit, has both constraint satisfying initial data and evolution, and has as a limiting case Maxwell's equations as well. So again, something that is readable and you can use. We also have a couple of arrangements that are in Canuda, but not in the Einstein toolkit. And one is this Canuda EDGB. What is this? This is one of these quadratic gravity models that allows to evolve scalar fields in scalar Gauss-Bonnet gravity. And the latest addition is Axi-Dilaton. Axi-Dilaton is a general two-scalar field model with coupling to higher curvature terms, and actually does include Gauss-Bonnet as well as just two scalar fields, potentially with a mass term, as specific cases. So it's really a parameterized numerical relativity code for two scalars with additional higher curvature corrections. And then the other arrangement that is under development is Canuda X. So this is our next generation Canuda code for the use with Carpet X. The space-time evolution code is basically done. Cheng has done the majority of the work. Lucas has also worked with us on that to connect it to the new multi-patch implementation. And it's basically ready to go. And I'm really excited to compare also to your new code and the benchmarks that you already mentioned. It also has wave extraction. So I think we will try to include that in the next release for the Einstein toolkit as well. Okay, so that's the landscape that we have for Canuda. I also wanted to give you a bit of an idea on what each arrangement looks like. And I will do this in the example of the scalar arrangement. So what do we have here? The first thing that we have is a thorn that's called scalar base. And in the base thorn, we will define all of our grid functions and their symmetries so that the code knows about that these grid functions exist. We also define here some specific parameters that we want the code to know about, like a scalar field mass, maybe if there's interest in different types of potential, and I don't know where Jake is, but here, yes, exactly. Yeah, so this is where these things could be defined. We define fall off at the boundary and so on. So this is basically setting up our grid functions. Then we have the initial data SON, actually two of them. One gives you analytical initial data, usually as a Gaussian profile, or a quasi-bound state solution that you can derive for a massive scalar field in GR background. And then we also have a code that Cheng and Giuseppe Ficara wrote that gives you constraint satisfying initial data for binary black holes with the scalar field, and I will actually talk about this when we talk about our extra fields. And then the big one is the evolution SORN that, as the name says, evolves the Klein-Gordon equation as a time evolution problem. It also writes the scalar field energy momentum tensor as input to what's called T-mu base, which is a translator to then go to the metric. So we basically write the components of the energy momentum tensor here so that it can be read into the gravity evolution SORN if we wanted to couple these two together. Okay, and some of the new things we have here is that we now have up to 8th order finite differences and so on. And then you also want to analyze your data, so we extended our wave extraction SORN so that it knows about contributions from the energy momentum tensor. Okay, so I didn't bring a tutorial here today, but if you do want to look at this, we have a tutorial from the Rochester workshop, and it's available here on this Git repository. Okay, so let me pause for a second and check if there are any questions about the setup, the code, structure itself. No? Then let's move on to the application, black holes and fundamental fields. Here I want to think about black holes interacting with scalar fields. Why do I think this is interesting? Well, there are actually two reasons. On the theoretical side, there is an effect called superradiant instability. And what that is the following. So if I have a rotating black hole and I have a low frequency bosonic field, so a scalar field or a vector field, scattering off that rotating black hole, that field can get amplified by extracting mass and angular momentum from my black hole. That's called superradiant scattering. If I have a mechanism that confines the field around the black hole, my, say, scalar field that has scattered off, amplified, is reflected back onto the black hole and will again superradiantly scatter, so will again increase in amplitude. So it will end up with an instability. The field will grow at the expense of the black hole mass and angular momentum. Now, one of the first ideas about this was really to put a mirror around this by President Tucholsky, who called this a black hole bomb. If you think about, can this really happen in nature? There are actually fields that if they have a very small mass, such that their Compton wavelength is comparable to the size of the black hole, that provide an effective mirror. And you can think about the superradiant instability as a mechanism to form condensates of very light scalar or vector fields. So this is why I'm interested in some of these things, because these light fields, as I will give you numbers in a moment, can actually be interesting in new or beyond the standard model particle physics. The other question that we want to think about here is, are there mechanisms that allow the scalar field to accumulate around the black hole through accretion? And one prime example is actually a nice paper by Ted Jacobson from the 90s, where he took a scalar field that's time dependent at infinity and put the black hole in there. So it's like putting your black hole into a bath of dark matter. And then it turns out that you can actually have black holes with scalar here. So I want to briefly talk about this as well. So this is on the more mathematical side. And then the applications, I just said, it's these fields that are subject to the superradiant instability or to this kind of accretion are very light fields. And some of these are interesting as candidates for dark matter. So this is maybe the physics interpretation. Also, I realized that some of what we have been looking at might be a good toy or a reasonable toy model to think about environmental effects, which then becomes important if you want to think about waveform systematics for, strong field tests of gravity. Okay, so this is why I care about these light fields. If you want to see the Lagrangian, it's here. We have our Einstein-Hilbert term, then the massive scalar field. So we have a scalar field phi with a kinetic term and mass parameter mu_s. In so not here today, I will not talk about a massive vector field, but we have the code for a massive vector field, and this is here. As I mentioned, through either superradiance or accretion, we can form a bosonic condensate around these black holes. Now, if you want to give numbers of where is this relevant, let's go back to this argument that I said, oh, the Compton wavelength of the field is comparable to the size of the black hole. We can actually also rewrite this in dimensionless form as black hole mass times mass parameter mu of your field. But more importantly, let's give some physical numbers to that. So if I take this ratio and put back in all my units, so go outside natural units, then this ends up to be 10 to the 10 mass of the black hole in units of solar masses, mass of the field in terms of electron volts. And if I say I want that number to be of order 1/1/2, then you can also make an estimate on which kinds of fields would I probe with this, right? So if I have a stellar mass or heavy stellar mass black hole like we observe with LIGO, then this ratio would tell me that I'm sensitive to fields with masses of 10 to the minus 12 electron volts. If I go all the way up to supermassive black holes with 10 to the 10 solar masses, then I might be sensitive to fields with masses of 10 to the minus 21 electron volts. So if I mentioned dark matter or wave-like dark matter candidates earlier, they live at the 10 to the minus 20-ish electron volt end. If I think about particle dark matter, they would actually go up to the more massive end. But in general, here, I'm really thinking about gravitational interactions between the fields and our background space-time. So I'm not invoking any coupling to standard model matter. I'm really just looking at the gravitational interaction and might be able to probe ultralight bosons in a large range of parameters. Okay, so the first part I want to look at is just single black holes. Now, I talked about the superradiant instability before without giving you a time scale. If I have a massive scalar field around a highly spinning black hole, that's when superradiance is the strongest. And the typical growth rate in the best case scenario is something like 10 to the 7m, so 10 to the 7 light crossing times. Well, doing that in 3+1 numerical relativity is completely hopeless. So we're not going this way. But one thing that we will see is that we can form scalar condensates through accretion. And actually, one of the first works that I've done by now 10 years ago, even more than 10 years ago, is to think about a scalar field around a rotating black hole. It's slowly decaying, but so slowly that, as you can see in the animation where I'm showing the amplitude of the scalar field in the equatorial plane, so the XY plane, the spin of the black hole is pointing out of this plane. And let me just show this again. So what we are seeing here is that the scalar field seems to condensate around the black hole and is dragged along with a black hole spin. Now, here we didn't do anything specific about our boundary conditions. Actually, we allowed the field to decay to infinity. But then a few years later, 2019, Katie Clough came back to this problem and said, well, and also thought about the Jacobson result of having a time-dependent scalar field at infinity. So what she did in this work was to impose boundary conditions such that your scalar field is oscillating at infinity, and the frequency of this field is determined by your mass parameter. And what they found in this case is actually solutions that are standing wave solutions around the black hole. So you might even think about this as black hole hair. And what I'm showing you here is a scalar field as a function of time. In the top plot without back reaction, so just a scalar field in this case a Schwarzschild background. And in the lower case, they included back reaction and constructed the full solution for this. Good. I also want to give a shout out to Jake's recent work because I think it's in a minute. First, I wanted to give a shout out to my own students. Sorry about this. So no, because Freddie Hancock actually extended this type of calculation to a massive vector field at the moment perturbatively, but we are definitely thinking about extending this also to time domain evolution, and this should come out tonight. So we submitted that on Friday, if you're curious. So now I can give a shout out to Jake's paper. I'm so sorry about that. So what they are looking at is a black hole in scalar cosmology. So instead of a mass term, you're thinking about a potential with 5⁴, which usually gives you an expanding, or can give you an inflaton, something like an expanding universe. And here I picked one of the plots. Next time I should ask you if there's any animation I should show on your behalf, where they were looking at the accretion rate of the black hole, so as a function of time for different parameters, multiplying your scalar field 5⁴. Yeah. Okay. So this is some of the recent work done with, well, except for the middle one, recent work done in numerical relativity with massive or scalar fields with a potential. Now the question is, what happens if I put this into a binary? And this is work that we are writing up with Cheng-Ching, Giuseppe Ficara, and myself. So here we really want to look at consistent evolution of a binary black hole inside a condensate of a massive scalar field. So at the moment, we're not asking how the scalar field got there. We just put our binary into this environment. And we also say, okay, let's for the moment think about a scalar field that is spherically symmetric. Yeah, take that as a toy model. And here, the first goal that we had was to actually try and see if we can use this to look for new types of particles. The second realization was that we can actually also use this as a toy model for environmental effects, and that I think will be interesting to really think about gravitational wave modeling for LISA, potentially also for LIGO. Okay, so the first thing that we did was actually write a constraint satisfying initial data solver to do that. And it's based off two punctures. And the solver is actually already in the Einstein toolkit and has been for a while. And I can tell you in a second why that is. So how do we go about this? We say, well, let's take a scalar field with a radial profile. We make it time symmetric. So we impose that its momentum is 0. That's an approximation, but it's usually a pretty good approximation. If we insert that into our constraint equation, then the momentum constraint is still the same as a vacuum momentum constraint. So that's good. And the Hamiltonian constraint is a vacuum Hamiltonian constraint plus additional terms due to the scalar field energy density highlighted here in blue. Now, with this, we can still use the two punctures approach because the momentum constraint is still solved by the Bowen-York curvature, extrinsic curvature solution. And we just need to find what our metric does by solving the Hamiltonian constraint. So we went ahead, did the usual York-Lagrange conformal decomposition of the metric and extrinsic curvature, use puncture data as an ansatz. So psi here is our conformal factor. Psi BL is Brill-Lindquist initial data. So think of that as a superposition of two punctures. And then U is a correction function here. So essentially going very much through a lot of the derivation that actually goes back to Steve's work with Bernd in the 90s. Good. So that's our ansatz. And we write down our Hamiltonian constraint, implement it, run it, construct the solution with increasing resolution, and see that as increasing resolution, we actually pick up noise, and the solution seems to become unstable, non-unique, you name it. So what's going wrong here? Well, we looked at our constraint a little bit more closely. So this should be an elliptic type PDE, right? Well, let's look at the linearized equation. And was looking back at a paper by von Choquet-Broha and York, who are thinking about well-posedness for elliptic equations, where you have your Laplace operator minus some function, and U bar here are perturbations, And this function h has to be positive. And if you look at our linearized equation here, we have the Laplace acting on the perturbation minus perturbation, and everything in the big brackets is this function h. And the first term is positive, great, but the second term comes with a minus sign. So if that second term becomes sufficiently negative, we actually lose ellipticity, and that means that we don't get unique solutions, and that was exactly the problem. So the way we fix this here is to say, let's actually also decompose the scalar field with a conformal factor, and then we estimated from the form of the equation what the exponent of this conformal factor should be, and found roughly this to be -3. And then we again constructed our solution and now found actually a unique solution that converged. And we also did a convergence test where we constructed our true solution with 160 collocation points in the two-puncture spectral solver. And what I'm plotting here is the difference between the solution constructed with n points compared to that reference solution. And we get very nice exponential decay here, so our solutions are converging. Okay, so with that, we could now go ahead and actually do perform our simulations of binary black holes. One thing that we did, and this is why it actually took much longer to finish this project than we originally anticipated, are two things. So the quick one was to implement 8th order finite difference stencils in both the space-time evolution and the scalar evolution for Canuda. That was fast. But we also wanted to have initial data that had low eccentricity, right? If we wanted to use it for data analysis for LISA or for LIGO, and we want to compare two quasi-circular binary black holes in vacuum, we better make sure that our binary black holes with a scalar field are also quasi-circular. And that's actually non-trivial. The first simulations that we did, we switched on our scalar field, put a mass parameter on the scalar field, and well, for a small mass parameter, it should still look kind of quasi-circular with the parameters that we used from the vacuum case. And then we increased our mass parameters, and we actually went from an almost quasi-circular spiral to something that looked like a plunge. So Cheng-Ching went back and very carefully did the eccentricity reduction, which actually took several months to do in this case. And now we have quasi-circular initial data with an eccentricity below a few times 10 to the -3. The simulation that I will show you here is for a binary black hole with a mass ratio of 1 to 2, and the scalar field has a dimensionless mass parameter of 0.2. On the left here, we will have psi4, so the Newman-Penrose scalar in the equatorial plane. On the right, we have our scalar field also in the equatorial plane. And we start off with a spherically symmetric scalar field profile. So the first thing that you see here on the left-hand side, we just get the junk. The scalar field itself seems to accrete onto each of the black holes, just like we saw for the single black hole cases. And as the black holes are orbiting, the scalar charges are following that motion and generate scalar radiation. And this is what you could see here on the right, or can see here on the right-hand side, as the binary black holes get closer and closer. And now we are close to merger, so the gravitational wave signal really increases in amplitude and frequency. And now at the merger, we have our burst of gravitational radiation, while the scalar field seems to still linger around a little bit and was slowly decaying. Okay, so this is a time evolution. Let's look a little bit in a little bit more detail at the waveform. What does the presence of the scalar field actually do? And this is a very busy plot. So this is for the equal mass binary black hole. We have the quadrupole mode of the Newman-Penrose scalar as a function of time. Different colors are different mass parameters. So let's zoom in around the merger. This is what we have here on the bottom left for those online. So bottom left, again, Newman-Penrose scalar as a function of time zoomed in around the merger. The black line here is just binary black holes in vacuum, so no scalar field. And the other lines correspond to having a scalar field with a certain mass. Blue is a mass of 0.2, orange a mass of 0.4, and 6 a mass of, green a mass of 0.6. And here we see something interesting, right? We see that some of the binaries seem to merge earlier, some of them seem to merge a bit later. And if you look at the unequal mass case, so this is corresponding to what we just looked at in the animation. Again, the full waveform in the top, psi4 as a function of time. Zoom in here in the bottom right, Newman-Penrose scalar as a function of time, zoomed in around the merger, same color coding, so vacuum is in black. And then we have a mass parameter of 0.2 in blue, 0.4 and 0.6 in orange and green. And in this case, we seem to see a delayed merger. So what's going on? And what we think is going on is that there are actually two competing effects. So one effect that we were thinking about first is that our scalar field charges in quotation marks, scalar field accumulated around each black hole acts like a charge. As our black holes in spiraling, we saw the generation of scalar radiation. So that carries energy away. So that should accelerate our in spiral, right? But then there's also an effect called dynamical friction, which we think would slow down our black holes and lead to a delayed merger. So I think what's happening here physically is that we have a competition of these two effects. And since we are really at a set up our initial parameters such that we are just about seeing these phase shifts, outside the numerical error, we can actually pick up both of these. Okay, so these are the results. As I said, we are writing this up now, and I think they are ready to be used for then a follow-up parameter study to really get a handle on effects of environments in the nonlinear regime of black hole mergers. Okay, so before I move on, let me pause and see if there are any questions from the audience.
For those results, was it it wasn't like a beyond GR scalar field, it was like a minimal coupling?
Yeah, so this was just minimally coupled massive scalar field. So here really not beyond GR, this is thinking about additional types of matter, right? So one of the physical motivations is that these scalar fields might be axion-like particles that are predicted in the string axiverse, among other things. So this is really coming from particle physics motivations. And I think in that sense, it's also complementary to your work where you were thinking about an inflaton that has a phi to the 4 potential, right? Yeah. Yes.
Wondering about the binary case, what is the boundary condition?
So here our boundary condition is outgoing for both fields. So both, if I say both fields, both the metric and the scalar field. Yeah. Okay. Any other questions? No?
And then initial data, use exponential fallout.
So the initial data, we took a Gaussian spherically symmetric. And we went through the construction that I was describing here. So it's constraint satisfying initial data in that sense that we start with a scalar field profile, solve the Hamiltonian constraint consistently, and then the eccentricity reduction was on top of that. So once we have our constraint satisfying initial data, we also went and checked which momentum parameters we needed to give to the black holes to have eccentricities below order 10 to the minus 3. Yeah. Okay, any other questions? Good, then let's shift gear and think about black holes in modified gravity. And actually, let me be a bit more precise because there is a huge zoo of what modified gravity's theories could be. So I'm focusing here on a class that I call quadratic gravity. So I'm really thinking about extending Einstein's equations with terms that are quadratic in the Riemann curvature. Yeah, so that's what we want to focus on here. And why do I care about these? Well, because they can be motivated in two very different ways. So you can either say, well, actually, let me start with the last argument here. They say, oh, I want to capture anything that goes beyond GR. I don't know what the modification is. So let me do something like an effective field theory expansion. And let's do that as a series in curvature. If you do that, you have, bless you, the standard Einstein-Hilbert term as your lowest order term, and then you would have Riemann squared, Riemann cubed, and so on. So let's take this as the lowest order in that expansion with a Riemann squared coupled to a scalar field. You could also say, well, this is kind of ad hoc. Can I get this from a more fundamental theory? And the answer is yes. If I take heterotic string theory, in 10 dimensions, I take the low energy limit and I compactify that from 10 dimensions to 4 dimensions. I actually end up with the same action. Overall, you can ask, we know two things. Einstein's theory is fantastic to describe astrophysics. It's amazing. But we also know that it breaks down if we want to combine gravity with quantum physics. So on a theoretical level, if we believe that there needs to be, or there should be a unified theory, then we also know that Einstein's theory is not a good description because it breaks down as a quantum theory. So quite likely there are higher curvature corrections. Good. So all of that led me to look at the model or some of the models that I'm writing down here. So the Lagrangian is really long. I will talk you through this. But this is the most general case that you get at the second order in curvature with scalar fields. So what do we have here? The first term is our Einstein-Hilbert term that we know and love. Then we can add a scalar field phi. We'll call that a dilaton because if you take the string theory version of my argument, it actually has a specific coupling like what they in their community call a dilaton coupling. And I couple the scalar field to this curly G here. It's called the Gauss-Bonnet invariant. It's a combination of Riemann squared, Ricci tensor squared, and Ricci scalar squared, such that the equations of motion that you get are still second order in derivatives. So nonlinear in those second derivatives, but second derivatives nonetheless. And this first part in green is what people usually call scalar Gauss-Bonnet gravity or Einstein-Dilaton Gauss-Bonnet gravity. If you hear Gauss-Bonnet, this is what we mean by that. Then we get a second set of terms with another field, zeta. Zeta is actually a pseudoscalar, if you think about how it transforms. And this pseudoscalar I will call the axion. And this is coupled to the Pontryagin density, so Riemann, a dual Riemann times Riemann. So this by itself is typically called dynamical Chern-Simons gravity. So if you have seen me talk, or if you have seen my colleague Nico Yunus from Illinois talk, he has studied dynamical Chern-Simons gravity a lot because you get, through the Pontryagin density, some parity violation in your theory, and you can study effects of that on black holes and gravitational wave emission. Now, if you follow this argument from string theory and you do this, compactification, long derivation, you actually end up with both of these types of terms, and they can be coupled to each other. So our purple here is a coupling function between the scalar or dilaton phi and the pseudoscalar or axion zeta. And what we want to look at for the results is mostly this axiodilaton gravity. But I will take a moment actually to talk about how can we solve, or how can we even begin to solve these theories numerically. Give you one result that's not our own, but it's a very nice paper. And then I will talk about our most recent results. Good. So why is it non-trivial to solve this? Because this orange term, Pontryagin density, actually gives you third time derivatives in the equations of motion. And higher time derivatives usually is bad, gives you ghosts, and actually it seems that we cannot find a well-posed initial value formulation for that, which we need for numerical stability. The situation is a little bit better for Gauss-Bonnet, where we get the second derivative, nonlinear second derivative terms, but people understand how to do this. So let's go through some of the approaches that the community has developed over the past, I would say, order 5 years to address problems of having higher time derivatives or equations that give you a mixed hyperbolic elliptic PDE. Yeah. And as I said, I care about this because we need well-posed initial value formulation, as a necessary condition for numerical stability. Okay, so first approach is maybe the easiest one, where we say, well, let's just, well, given the motivation that we have, these corrections to Einstein's equations are probably small. So let's make that explicit, and let's expand both our metric and our scalar fields in the coupling parameter as our small parameter. If you do that, you will end up at each order in this expansion with the metric G at order n acted upon with the Einstein operator. So really just our wave operator for the metric in appropriate coordinates. And all the corrections enter at a lower order. So they really just give you an effective energy momentum tensor. Likewise, for the scalar field, you get a scalar field at nth order acted upon with a wave operator from the background. And then you get a bunch of source terms that may contain curvature terms, but constructed from a previous order. So here you get a set of wave equations for both the metric and the scalar field with some source terms. Well, that we know how to deal with, right? So this is very nice, very easy to implement, because all the corrections really just enter as some effective energy momentum tensor or source. It's nice if you want to look at single black holes. It's also useful if you say, oh, I have these additional fields in a binary, I can compute the scalar radiation and estimate, and this is important, estimate how this affects my metric. If you really compute the second order for the metric here, you actually end up becoming inconsistent, because your modifications, if you have a single black hole, is fine, right? But if you have a binary and you change your metric a little bit and you don't communicate that back to your background metric, eventually you will have a accumulation of this extra field of these modifications without ever consistently bringing this back to your metric. So for full binary simulations, this is not a very good approach, but if you need to start somewhere, this is not a bad start. And actually, this is what people in the community have done first. I also have to admit, for what I'm going to tell you about, I will work in this approach, but I'm mostly thinking about single black holes. I think we're okay. If you want to go beyond that, there are two other main approaches that are being used. One is inspired by relativistic hydrodynamics. So in relativistic hydrodynamics, if you have relativistic Navier-Stokes equations, you have a derivative expansion in your fluid variables, and you can end up with an acausal theory. So people in hydrodynamics actually already figured out how to do this by introducing an auxiliary variable that allows you to drive your solution, drives your system to the right solution. And in these modified high curvature theories, you have a very similar structure. And that's something that Luis Lehner, Nestor Ortiz, and Cayuso had realized. And they said, well, okay, let's do this in a toy model first. So the structure for scalar Gauss-Bonnet is like this toy model here, where I have a wave operator acting on my scalar field. And then I have force spatial derivatives acting on my scalar field, or on my field. If you implement this toy model, you will get superluminal modes, right? Causality, and not really the physical system that you're interested in. Now, how can you fix this? As I said, let's take inspiration from the Israel Stewart trick, and let's introduce a new quantity called pi, which is just a second spatial derivative of our scalar field that insert this into our original equation, gives us a wave equation for the scalar field related to pi, and we come up with a wave equation for this auxiliary variable pi, which now has a definition, but also has an additional term that helps you regularize and go to the real solution. So this equation is a little bit ad hoc, but it seems to work well in practice. So this is what is being done in hydrodynamics, and this is something that Ramiro Cayuso implemented for effective field theories of gravity, and also could perform successful simulations. There's a caveat that there's actually a bit of a dependence on what this time scale here is. Okay, but you know, if we want to do something better than the order by order, then this is the next approach that one can try, and this has been successful. And then the other kind of breakthrough in this context came from mathematical work by Aaron Kovacs and Javier Real, that they introduced a modified generalized harmonic gauge. So essentially what they took was not just one metric, but they also introduced two auxiliary metrics, such that all your fields would move causally within one of these auxiliary, either the metric or auxiliary metrics. And that has been implemented and is actually been very successful to really compute gravitational waves from binary black hole mergers in scalar Gauss-Bonnet gravity. Okay, so I actually want to show you a work by Max Corman from last year where she simulated binary black holes similar to GW 150914, so the first binary black hole merger that LIGO ever detected, but in the scalar Gauss-Bonnet gravity. And she compared, on the one hand, the full solution with the order by order expansion. So what we have here is the 2-2 mode of this gravitational wave strain as a function of time. We have GR in black. Also here's the inset. Then the dashed lines are the order reduction, so the order by order scheme. And the dashed dotted lines here are the full scheme. And what you can see, especially from the inset here, is that the full simulations seem to perform pretty well. The order by order expansion, one is here, the other one actually exceeds here. So you really get an over amplification, and this is due to the secular effects that are partially non-physical that I mentioned earlier. Okay, so this is order by order expansion. She also compared to this fixing idea. So again, the 2-2 mode of the strain as a function of time. And here in green and dashed is a full solution. And dashed dotted and dotted lines are with this fixing where capital T now here is related to this tau, so the time scale over which this happens. And what you can see here is actually a dependence on the time to merger, or the phase evolution, if you wish, on this extra parameter. So you also want to be careful on how you're setting this, and that you're really in a regime where your results are independent of this time parameter. But also, if you can solve the full system, that really is much better for your modeling and can be used for waveform modeling. Okay, so I've been talking a lot about this, but do give me a couple of minutes. I mean, we still have 13, but let me take 5 to talk about our results, coming back to this really complicated quadratic gravity theory. Now we are working in the decoupling limit. So by that I mean that we have a scalar field that gets information from the space-time metric, but is not talking back to it. And this sketch actually goes to one of my graduate students who created this for precisely these purposes, to explain what do we mean by decoupling. So what we are going to do is think about or simulate the scalar fields phi, pseudoscalar theta, in a background of a single rotating black hole. And this paper has just been accepted. It's now in press and PRD. Good. So this is going to be a bit of a busy slide, but thinking about what does a scalar field do if we put those around a black hole. Well, for the scalar field itself, we will have scalar hair sourced by the Gauss-Bonnet invariant. To leading order, it's going to be a monopole. From the dynamical Chern-Simons term, or the Pontryagin density, we will get a source that goes like, for the theta field, that goes like the Pontryagin density. So that actually gives you an L equal 1, M equal 0 dipole, just like we've sketched here on the side. And the form of these solutions are listed here. Now, these were for the individual series. We now want to couple this together. So the dilaton and axion are talking to each other. If you do and compute these solutions in the small coupling, small spin approximation, you can do that analytically, and you end up actually with the decoupled fields. So in that solution, they don't know anything about each other. So one of the questions that we wanted to address is, how does the coupling between the scalars affect the formation of scalar hair, and how does high spin affect this formation of scalar hair? What's the end state here? Because that's something that we cannot capture analytically. So what we've been solving is really this set of equations that we have down here with our Canuda code for axial-dilaton gravity. So this is a parameterized numerical relativity code for two scalar field models coupled to gravity. Has limiting cases through simple parameter settings from minimally coupled single or two scalar field models, Gauss-Bonnet, Simons, and axial-dilaton gravity. And let's actually look at the evolution of these two scalar hairs. The background here is a Kerr black hole with a spin of 0.99. We are using for the background the Thorne Kerr and quasi-isotropic coordinates, and then we are evolving a scalar field on top of that. We initialize them as 0. So we really see how the hair forms. On the left-hand side, we have the scalar field in the plane that's parallel to the spin. So perpendicular to the equatorial plane, and the axion field here on the right-hand side. And as we see the evolution here, the dilaton has, well, to leading order, the monopole, but we also see something apparently missing. Turns out the full solution actually has a quadrupolar contribution with a minus sign. We actually see this here in our simulations. And on the right-hand side, we really get our dipole, leading order dipole field now evolved together. Okay, yeah, I can briefly talk about this, just thinking about how this changes with spin. So here we have the scalar leading order scalar field multipoles, the monopole, 0, 0 as a function of time. Different colors are spins from 0.1 to 0.9, and we clearly see here that the monopole, first of all, grows from 0, overshoots a little bit, and then approaches a constant in time value, and that amplitude reduces as I increase the spin. The opposite is true for the axion. Again, the leading order contribution is a 1, 0 multipole as a function of time. Color coding for the spin is the same, a bit of overshooting in the beginning, and then the axion field also settles close to 0 for a very small spin, as we might expect, and then the amplitude increases as I increase my spin. So the trends are all consistent with a small coupling, small spin approximation, but now we actually get the full configuration here of the two-hair solution for scalar fields in this axial-dilaton gravity. Okay, let me move on here. Just the last thing to show, it's a proof of principle simulation of a binary black hole in the background, where we have two equal mass black holes that are not spinning. Separation is 6m, so it's really just, you know, a couple of orbits before they merge. 0 scalar fields, so we see how the scalar fields are excited during the in-spiral, and that's something that we actually want to look at in a little bit more detail with Deborah. I swapped axion and dilaton here. So what we see is the following. We have our dilaton hair here growing before the merger as expected, and then form a monopole mostly after the merger. But let me actually rerun this and look at the left-hand side. So here, we shouldn't have an axion field because the black holes are not spinning before merger. But there seems to be a hair excited as we go close to the merger. So I think the angular momentum generated in the very late in-spiral is enough to excite here the axion field. And as I said, this is proof of principle. So in the upcoming work, we are really looking much more carefully about the scalar radiation that's generated here. Good. So let me just finish here. I told you a little bit about applications of numerical relativity outside just binary black hole mergers. Talked about black holes in light fields and black holes in quadratic gravity. And I leave it at that. Thank you very much. Thank you.
Is there any questions from y'all?
Has there been any work look at kind of how a penalized Gauss benefit where the connection is not treated as like a Chibita, but as a generic connection? set of additional field equations.
Yeah, so I'm not aware of anyone having done this. Oh, sorry, repeating the. Yeah, I'm sorry on that. Yeah, so the question was if anyone has looked at scalar Gauss-Bonnet gravity in the Palatini formulation where you treat your connection as an independent variable. And my answer is I'm not aware of anyone having done this in numerical relativity or even writing down the equations just without doing the numerics. So I'm not very much aware of that. Yeah, but that's a very good question. Thanks.
You want to have like one block relation. So you don't disturb the predictions of the Einstein set. But it turns out that if you release the connection from that thing now has 13 terms because the curvature tensor is no longer in symmetries.
Okay. So again, for everyone online, I think the comment is it's interesting in the context of making connection to a Lovelock gravity, which is the most general theory of gravity with higher curvature terms. The point is, so let me make one point and then I finish your comment. So if you only have Lovelock gravity, you get things like Riemann squared in the next order. But if you don't have a coupling to a scalar field or coupling to matter, these terms are actually only topological if you're on 4 dimensions. So there you would have to go to at least Riemann cubed, or you have to have coupling with matter. So this is why people haven't really looked very much at Lovelock gravity. And then let me finish the comment that you made. So if you do look at Lovelock gravity with Palatini, you say you get at least 13 extra terms because you're losing the symmetries of your Riemann. Yeah. Okay.
Let's thank our speaker again.
Thank you.
And we will have another coffee break and following with Steve's tutorial at 3:30.
Good. Can everyone hear this online? So we are continuing at 3:30.
Thank you. Thanks very much. Yeah, so for people online, we will resume at 3:30 with the tutorial on Einstein fluid. Yeah, I think you're.